Welcome back to another thrilling, exciting Math 168. Today we're covering section 2.6. We're going to do the quantitative variable, and we're going to speak specifically about linear regression. So, as normal, you'll want your calculator on hand and probably access to StatKey at the same time. I think we'll jump back and forth a little bit. So in section 2.6, it's a two quantitative variable. Remember, quickly on a review of a two quantitative is a scatter plot is our means of visualization. And in addition, we look at the R value or the regression of that equation. To have a positive regression or a positive R fit was to have an increasing X and an increasing Y, and to have a negative was to have an increasing X but a decreasing Y. The stronger the number was, the closer it was to 1 or -1, and the weaker the association was, the closer it was to 0. And we studied some of those in the last chapter. So we want to use a regression line to predict the values of the response variable. That's really the goal of creating a regression equation. We want to calculate residuals, residual meaning leftover. We want to interpret slope and intercept. You're going to have to make a little bit of recall from your previous days of mathematics, middle school, high school days, to where y equaled mx plus b was very much in the forefront of what you were doing. So for instance, in y equaled 2/3 x plus 7, the slope would be 2/3 and the y-intercept would be positive 7. However, though, we tend to think more in terms of the intercept being the important feature to start with and the slope being the secondary feature. So in statistics, we perform the reversal, or we change the position of those to where we put the 7 first because we want to know a starting place of our line, and then we want to apply a 2/3 slope to every x variable or every explanatory variable that's inserted. And it's important to understand those pieces that I'm talking about right there when I am saying that, in that 7 being the value that you are starting with will be influenced by a change in rate or slope of 2/3 because of every explanatory variable. And what we're really trying to do is we're trying to make a prediction on a response variable. The letters pretty soon will come out and they won't matter because we're putting words in there. Can you estimate the temperature on a summer evening just by listening to crickets? Find a straight line that best fits the data in a scatter plot. Well, if this is the data here, and the number of chirps are on the explanatory, and the temperature is in the y, or the response, it looks pretty close that it forms a very nice linear equation, or a linear prediction, if you will. And if we put in this line, what we're referring to as a regression line, we can make predictions based on this. Something to note is there are no data points on the line that we create. There's no data in between this data point and this data point here. These data points are not connected. So between 120 and like 150-ish, no measurement was taken at 140. But our prediction line can clearly say the trend being, and I can look for a trend in data at 140. Now in StatKey, we can also see these very same things. So if I'm looking at two quantitative, and I think cricket chirps are probably in the data set. It's the second one down. You'll notice here's the same data that's being presented to you by me. And if you show the regression line shows that line of that trend. Also notice in the bottom right-hand corner, three very, very important things. A correlation coefficient of 0.991, very, very strong and positive. A slope of 0.231, and a y-intercept of 37.679. When we identify the explanatory and the response variable, it's quite easy. The explanatory is always on the x-axis, and the response variable is always on the y-axis. We're always using some change in x to predict some change in y. The equation line to estimate regression. We make some slight changes, and like I said, the letters really don't matter that much. But the analyzation here being that the predicted value that we're looking for on the y-axis, that's going to be the y-hat value. We're looking to predict this number mathematically through an equation. A is our starting position, and I guess I'll do a little typing here. A is the starting place, or also known as the y-intercept, right? So the starting place on the graph is the y-intercept, or the starting place, and the b value is the slope of the equation. The slope can also be justified as the rate of the equation, and that's my b value. The explanatory x drives the prediction y. These will be data points or points that we create. The a will be a value of start, and the b will be a slope that we change by. Here's a typical example of a regression equation. It says the regression equation can be used to predict y for a given number of x. And this goes back to the cricket chirps and then the temperature outside. Now, I want you to notice a couple things here. Notice the starting value is 37.7. And if I go back to Stack real fast, remember 37.7 was the y-intercept right here. If I look at the slope now being multiplied against chirps, so the number that's affecting some explanatory value, chirps, 0.23. If I go back here, 0.23. The slope and the intercept are directly inserted into the regression equation as the y-intercept, and the y-intercept being the first value, A, and the slope, B, which is always multiplied by some term, and I'll put a little parenthesis there so you understand that's being multiplied by that. And that part is the explanatory variable. It says if you listen and hear cricket chirping about 140 times per minute, your best guess at the outside temperature is, so you would insert a 140, you would do the math, and 37.7 plus 0.3, which is the slope, multiplied by the explanatory variable, 140, and this is where the insertion took place, will yield a prediction, not an actual data point, but a prediction of 69.9 degrees Fahrenheit. Now, if we look at that on a graph, and the graph is this graph here, if I went straight up to 140 and I looked for the intersection, it looks like 70 degrees on the graph. 140 intersects vertically and horizontally with 170, or 70, not 170, 70, and we got 69.9 degrees mathematically. The graph gives us a very good idea of where the intersection would happen on a prediction. Remember, this data value did not take place. This is an x value that we are predicting a y value for. In a prediction, we would not use y, we would use the word temperature, and notice the temperature with the signature of like p hat. We would use temperature. This tells us that this is the predicted temperature. Would be equal to 37.7, the starting position, plus 0.23, which is the increase in temperature per one chirp. And I'm going to say that one more time. This value right here is interpreted as an increase of 0.23 in temperature, because remember, that's what we're predicting. An increase of 0.23 in temperature for every one additional chirp. If I were predicting this over here, the prediction is that the temperature is 37.7 degrees when there are no chirps. Because if we take this completely out of the equation and we multiply by 0 chirp, 0.23 goes away, the starting temperature is 37.7. So therefore the prediction is that if this takes place in solo, it will be about 37.7 degrees if no chirps are heard. Question is, what is the predicted temperature in 2 decimal places when the crickets do 103 chirps per minute? Okay, so maybe take yourself a second and go off to the side and do that. Okay, now that you're back, so we're going to use those values and we're going to We're going to put those into what we're doing here. So we have 37.7 degrees. Remember, we're doing a temperature and we're finding it. We had 37.7 degrees. That was our starting position for our y axis, or our beginning. And to that, we are going to add 0.23 for every one additional chirp. So notice that I use a set of parentheses there, and we're going to put 103 in for that for our calculation. Okay, go outside, go grab your calculator, put 103 in there, do the math, and your temp prediction will be 61.39 degrees. 61.39, and I need to put a degree symbol on there, and this was in Fahrenheit. I do need to use units when I'm making my predictions or my analysis. Okay, keep that number. We're going to need that number. So we know that 61.39 degrees Fahrenheit is a good number for here. 61.39 degrees. Jeez. Now, one of the cases in the cricket data set was 103 chirps per minute, and it gave 63.5. So if I go way back in the data set that this came from, and I don't know if we don't actually have that data set, sorry. One of the actual predictors in that data set at 103 was 63.5. Actually, we can see that. If we go into here and we go to the data set and we float over them, right here, 103 is 63.5. So that is an actual measurement right there that you can see. Okay, so let's go back. This can be written as, okay, well, the way we would write that is we would write exactly in X comma Y format. So in the X position, we would write the value of 103. And in the Y position, we would write the 63.5. Now, this is known as an observed mark. It's an observed mark because it actually took place. It's not a prediction. Okay, so make the notation between what is observed and what is predicted. The question is, how far is the predicted temperature from the observed temperature in this case? So from the slide before, the prediction was that if we put in 103, we predicted 61.39 degrees. So our prediction was on 103 measurement, and let me get my text box back, on 103 measurement, that we would get 61.39 degrees. So really what we're looking for here is how far off was our prediction from what actually happened in reality. Okay, so if we took that off to the side, and let me go get a little bit of wiggle room here to where we can do a little bit of math. So we have this value that we're taking a look at, and we're measuring, and we're trying to see, okay, what the heck is the difference between these two things? And when we have a line of prediction and we have a data value and we're predicting something here. So this is a prediction because it's on the line. This is an observed value here. The difference between these two things is what we're talking about. We're talking about in a vertical fashion, how far away did we miss by? And did we miss by a number that was above, or did we miss by a number that was actually below? And they can be either one. They can be above or below. Okay. So the question is, how do we find this best fitting line, and how do we actually get this predicted temperature? And that's what we're going to do right now. So this predicted and actual value. The observed response value y is the response value that was observed for a particular data point. You actually have this in your data set. And I'm going to put that in here. This is a data set value. And it's an x comma y. In a predicted, you use the model or you use the equation in order to come up with an estimate. The predicted response of y hat is different than the actual observed value y. It says the best fit line is that which makes the predicted values closest to the actual values. And that is always the case. We always want to have the line as best as possible. Now, you won't be making the line. You can see that StatKey does a wonderful job of making the line. And I'm going to show you how to put the line in your calculator additionally so that you have both resources available. This is the best fit line. This regression line is the best fit line. They are the same thing. So let's use this word residual. When I was speaking to you here, the distance from here to here, or the distance from here to here, this is the residual. The residual is the difference between an observed value and a predicted. An observed and a predicted. This one will have a negative residual because it's below. This one will have a positive residual because it's above. The way to calculate a residual for any data point is to take the observed number and subtract away the prediction. Okay, so y minus y hat. The residual is the vertical distance from each point in the line. I just showed that to you. So whenever we're calculating, we have to make sure that we calculate what we observe in data minus what we calculate mathematically. And we can't turn those two things around because if we do, we're going to have bad data. So here's that picture I was drawing for you in better terms. So the data point that we had was 63.5, right here, 63.5. That was the observed measurement, and that's right here at the top. However, though, we predicted a 61.39. Which means there was a residual value of 2.11 that was unaccounted for. And it's positive, which means the observed value was above the predictor line. If the residual was negative, then the observed value was below the predictor line. And you can see in this graph, we have some below and we have some above. This would be a negative residual that I'm up on. This would be a negative residual. This would be a positive residual. This would be a positive residual. We want these residuals to be as small as possible. Why? Because the closer the prediction and the observed, the better the line of fit. If the residuals are very large, then what that means is that it's not such a great best line of fit. Hence, a small R value. How would you do this? Well, mathematically speaking, we would do this right here. We would take all the y's, we would subtract all the predictor values, and then we would square them, and then we would come up with a sum of all them. So you can imagine if I have a couple of hundred data sets or a couple of hundred data points, this could be very, very, very busy, if you will. So we're going to rely upon technology in order to calculate this value. We're going to calculate a least square regression line. Now in StatKey, it's as easy as clicking the button and looking at the data set. So any data set we pick, let's just say restaurant tips, automatically I can see the correlation number, but I can also see the slope and I can see the intercept. So I'm going to record those two numbers real quick. I have a 0.182 for my slope, and I have a negative 0.292 for my y-intercept. Okay, well, so what does that mean for me? Got to scoot myself over so you can see me. So these are the two pieces of data that I just pulled out of there. Well, remember what we're focusing on here is y hat equals a plus b x. This is the regression equation right here. Okay, well, the m is this value right here. This is m. And the a is the y-intercept. So my prediction equation turns into negative 0.292. The slope is positive, plus 0.182 82 times X. But hold on, I'm going to go back and I'm going to figure out what was on X, and it was the bill. See it right here? The bill. So I can actually increase this equation to be a little bit better than it was. What was it predicting? It was predicting the tip. All right, I'm going to give him better. The tip prediction is equal to 0.292 plus a slope of 0.182, not times every X, but times how much the bill actually costs. The prediction of a tip will be equal to the starting value Y plus the slope multiplied by the amount of the bill. So for us, the temperature was equal to the starting value plus the slope multiplied by the chirps. The explanatory and the response. Unlike correlation, remember when it was in correlation, I could flip the linear regression and it didn't matter? In regression equations, it absolutely positively it matters. You can't flip the data and expect it to yield the same results, because it will not. If I go back to StatK real fast, and okay, so if I flip these, watch the correlation, 915. If I flip 915 didn't change, but watch the slope, 4.5 and 5.4, they flip. They change dramatically. They are not even close to being the same, but the association remains the same. As one increases, the other decreases. That doesn't change. But slope and y-intercept are affected dramatically. So the regression equation is always going to be the predictor y hat is equal to a plus bx. Remember, the slope is going to be in terms of every unit of x. When I was using my words here, the tip will increase by 0.182 for every $1 of bill. And if I go here, and if I were to talk about the y-intercept, the y-intercept will be negative 292 when there is no bill at all. Now, does that make sense? We'll talk about whether that makes sense or not soon because of that negative notation right there. The intercept is predicted at a y value when x is equal to 0. So here, the slope of 0.23. The predicted temperature goes up by about 0.23 degrees Fahrenheit for every increase of one chirp. When you're asked to interpret slope and intercept on your exams and quizzes, this is what you're looking to create. This exact wording or something super similar to this exact wording that means the same thing. What does the intercept mean? The intercept says the predicted temperature when crickets stop chirping or there are no chirps will be 37.7 degrees Fahrenheit. Regression cautions. Do not use the regression equation or line to predict outside the range of x values. This is called extrapolating. In other words, don't leave and be extreme with what you were given. If your smallest value is 50, don't try to go to 0. If your largest value is 50, don't try to go to 200. If none of the x values are anywhere near 0, then the y-intercept is meaningless. Remember back here, I had a negative number on my bill. Okay, well, if I went back to that data and I looked at that data to see what was going on, and I looked at those values, I'm kind of far off here, and I'm getting that. It's not really because of that. It's more associated with why it's a negative number. Oops, hold on. Let me switch my variables back. Right here. So I'm kind of close on a bill at $1.66, but what happens is it doesn't make sense because nobody leaves a tip when there's no bill at all. Computers will calculate regression line for any of the two quantities. Always plot your data, and the regression line equation should be used if the association is approximately linear. Outliers can be very influential on the regression line. Very influential. We have a couple more regression cautions. Higher values of x may lead to higher predicted values of y, but this does not mean it will change x will cause y. Causation is not part of this. Causation can only be determined if the values of the explanatory were determined randomly and it was an experiment. Question number 4 in Wiley. Let's do some of these problems and let's see what we can actually calculate and come up with here. And I'm going to get myself to a place where I can do a little bit of writing for you. So we have a number of hours spent studying on exam, and it's equal to the grade predictor, I should say, is equal to 41, which is my starting position. And I'm going to add to that 3.8 points times every unit of study. And I'm not sure what the units are yet. It doesn't really tell me right now. Question A says also that a data point for a student who studied for 10 hours and received an 81 on an exam. So that is an observed data study right there. Okay, number 1, find the predicted value for the data point and compute the residual. Okay, so first of all, this is our equation for our grade. We're going to start at 41, we're going to go up by 3.8, and this is the observed. They want us to find a predicted value. So they want us to put a 10 into the equation and do the math. So the grade prediction for 10 will be 41 plus 3.8 multiplied by 10. Well, do the math, do what you got to do, but remember that 3.8 is really 38, and 38 when added to 41 is going to be 79. So we have now a predicted value. So we have two different values here. Now, remember what we want to do here is we want to look at the residual. So the residual is always going to be, remember, it's the observed. So the residual is the observed take away the prediction. It's always what you actually have for data, take away what you think you have for data. So the observed is 81, and the actual value was 79. So the residual is positive 2, meaning the observed value was 2 greater than what we thought it would be under a prediction. So we found the residual and we calculated it to be 2. Interpret the slope in context. The predicted grade is, okay, so look at it. The predicted grade, okay, is, now what's happening here? It's going up by 3.8. So the predicted grade, and I have to get my text box editor happening here. Here we go. I'm going to write that the grade increases by about, always use the word about, 3.8 for every, it does say hours, for every 1 hour of added. It's important to say about 3.8, and it is very important to say for every 1 hour of the explanatory, which is study. Does the intercept make sense? 41. Well, when we talk about that intercept, it's completely possible to get a 41. Now, obviously, a 41 is probably not a passing grade. I mean, a person who studied for 10 received 81. We don't know these are percentages. I suppose we could surmise that. But could we say that if a person didn't study, they were getting a 41? So I would say, yeah, probably. This does make sense that this could take place. So yes, no studying. Score, or no, excuse me. We could predict a score of 41 because that's what the y-intercept was. Number 10. Number 10 says that, I gotta scroll down a little bit so we can see it. A study that examines several variables in collegiate football players, including the variable years, okay, which the number of years playing football, and the variable cognition, which gives the percentile on a cognitive reaction test. So what they did was they took people playing football, they measured the number of years, and they're measuring their ability to respond onto a cognition test. The scatter plot for these two variables gives the correlation negative 0.366. So first of all, that tells you that as the number of years increase, that the cognition is decreasing by 0.366. The regression line for, the 366 tells you it's a negative correlation, not by 366. The regression line for predicting cognition from years is cognition, that's your prediction, is equal to 102, that's your starting position, minus 3.34 times every number of years. Okay, so predict the cognition percentile for someone who has played football for 8 years. Okay, so let's switch here and let's go to here. So now we're on to football. So the first thing we need cognition. And to predict cognition, we start with 102. We subtract 3.34 for every number of years added to playing. Our first question is we are to get the prediction for someone who has played for 8 years. So we're going to do the cognition for 8. It's 102 minus 3.34. We're going to multiply that by 8. Go push that into your calculator. So 102 minus 3.34. I'm going to multiply 3.34 times 8, and I'm going to get 75.28. 75.28. Then it goes on to say there's more in the question. And for someone who has played for 14 years. Okay, so let's go back and do it one more time. So let's do 102. Let's do 3.34. This time let's put in 14. Let's push those numbers through, and 55 something. 102 minus 3.34 times 14, and 55.24. 55.24. Okay, so those are the cognitions, and you can see there's a decrease as the years continue to go on. Interpret the slope in terms of the football and cognition percentage. Okay, so we're interpreting the slope of negative 3.34. So in my text box over here, let me see, cognition will decrease, got to use the word decrease, by about 3.34. This is percentage in here because it's cognition. 3.34% for every 1 added year of playing football. Something like that, but it's got to say all those things. All the participants had played between 7 and 18 years of football. Okay, is it reasonable to interpret the intercept in context? Why or why not? Okay, well, when we look at this, okay, so they had played between 7 and 8. 7, remember, when we talk about a y-intercept, we're looking at something with an x value of 0. Okay, so first of all, 7 is not very close to 0. Secondly, you can't have 102 cognition. So two things are against us. One, 0 is far removed from the 7. And secondly, we have a cognition above 100%. So the answer is no for those reasons that I just explained. Mostly that 7 is too far away and that over 100% is not available. Summary of least square regression. For a quantitative response y and a quantitative predictor x, the least square regression is y hat equal a plus bx, where the slope is b and the y-intercept is a. Remember, the letters don't matter. What matters is what's being affected by what. To calculate a residual, it's the observed minus the prediction. We're going to rely on technology to find the least square lines, and I'm still going to show it to you with your calculator before we go. And the slope is the intercept as it changes the predict response when the explanatory x is increased by 1. Again, that keeps coming back, right? When it's increased by 1. Don't extrapolate. In other words, don't go far beyond what the model is built for. Estimate the least square regression line does not mean there is a linear trend in the data, okay? Estimating it does not necessarily mean there's a trend. Watch out for outliers. They will come back and bite you. Even a strong linear fit does not imply cause-effect relationship. Always look at the data on a screen and see what it looks like. So here goes a question. And I encourage you to stall it for a second and read it and then come back to it. There's a lot of words in this writing, and it talks about a lot of things, but it goes on to talk about 3 things. 1, it talks about the growth percentage in the country. 2, it talks about the national debt percentage, GDP, and it also talks about the federal deficit in billions. The question says, use StatKey or other technologies of the 3 cases to find the regression line. Okay, so we want the regression line for predicting the GDP. Now notice that they're using the word predicting. I'm going to draw that. Predicting the GDP. So that's a Y value. From means my explanatory is about to happen, from the growth rate. Okay, so the growth rate has just become my X value. And predicting this has become my Y value. And this over here really doesn't mean anything for the question I'm currently working on. What they want from me is they want a ratio to be equal to some starting value Y, some value of slope multiplied by growth. And since you see growth here, growth has to be the explanatory. Okay, so here's what we have to do. We have to take these numbers and we have to calculate them, okay? So get your calculator, write these numbers down, and we're going to use them just as they sit. Now, it's important that this is X and this is Y. So in my calculator, I'm going to go to my stats, and I'm going to enter this data into my stats that I have, okay? So I have data in here. I need to get rid of this data. You're going to use my second memory. I'm going to clear all my lists. I'm going to make everything go away, and boom, it's all gone. So I'm going to go to stat. I'm going to go to edit, and I'm going to enter some numbers. So let's put in 2.8, put in 3.3, and let's put in 3.9. There's my first set of numbers. Then into the L2, 76, 66, 55. So you've got X in L1, you've got Y in L2. I'm going to go back to, well, first of all, I'm going to do something that I didn't do that I should do. I'm going to go back to my stat plot. I'm going to turn off all my plots. You can see I got some plots turned on. I'm going to go down to number 4. I'm going to turn off all my plots. Always a good idea to turn off your plots when you're done, and I didn't do that from last time. Okay, so I have that data sitting in there, all sit in L1 and L2. I'm going to go to stat. I'm going to scoot over to calculate. I'm not going to run a 1 variable statistic. I'm going to go down to number 8. Look at number 8, linear regression A plus BX, exactly what we've been talking about for the past 30 minutes. Okay, A plus BX. I'm going to hit enter. I'm going to make sure it says L1 for X and it says L2 for Y. I'm going to scoot down and I'm going to hit the button. Let's notice a couple of things. First of all, let's note that it tells me that everything is in the form of Y equals A plus BX. It also gives me a value of A, and it says that's 129.219, or depending on what we're rounding to, it could round up. So I'm not sure what the problem says, but I'm going to go with 129.22 right now. The B value is negative 19.1 if I round. At the same time, I'm going to jot down the R value. Look how good that thing is. Negative 0.99999. It's almost a 1, right? So I'm going to go back here and remember what the question was. The question was for me to write the equation. Okay, well, how am I going to write that equation? Okay, well, everything I need is right here. So this came right from the calculator screen. So it's going to be, remember, y is my predictor, and there's words, and we'll use words in a second. Y is equal to the starting value, 129, and let me go back and check the criteria here. We're supposed to have round the y-intercept to the nearest integer and the slope to 1 decimal. So we're going to leave 129, and we're going to subtract 19.1 because it said for every 1, and we're going to multiply that times every x. But we're actually going to put words in for here and words in for here. This is my regression equation. So I'm going to go back. I'm going to do a little typing here. The ratio prediction is equal to 129 right here plus every unit of growth, and this unit of growth actually happened to be negative, so actually you could take out the plus before and just write minus if you want, but it's 19.1 times every unit, 1 unit of growth. Hopefully this has been useful to you. Your calculator is a powerful tool for creating these types of situations. Remember that in your calculator, everything has to be designated in the form of x and y. And I would highly recommend to you to use x as L1 and y as L2. When you run the regression equation, remember it comes from stat, comes from calculate, and it comes from number 8, a plus bx. Don't confuse it with number 4, which is ax plus b. That's a completely different regression. We'll be back next time. We're one chapter away from finishing chapter 2, or one section away from finishing chapter 2, and we will look at visualization of the last data that we have in this section. Winding ourselves up, getting ready for exam number 2. I will see you soon. Have a good day. Enjoy yourself.